All right, today we're going to be talking about finding the determinant using cofactor expansion. So before we talk about cofactor expansion, we need to talk about a really simple example, which is finding the determinant of a 2 by 2 matrix. So if we want to know the determinant of this matrix here, because it's 2 by 2, it's super quick and easy to do. All we have to do is take this diagonal, A times D, and subtract the other diagonal, B times C. And that's our determinant. And so a quick example here, say we have 1, 5, 3, 7, just making up some numbers here, and we want to know the determinant of this. All we have to do is do 1 times 7, which is A times D, minus 3 times 5. And so this is just going to give us 7 minus 15, which gives us negative 8. So the determinant of this matrix here is negative 8. And so you saw how quick and easy that was. And so if we're given a matrix that's bigger than that, so say we have a 3 by 3 matrix like this, how are we going to find it without being able to use this trick? And the way we do this is that we can reduce this 3 by 3 matrix into a bunch of 2 by 2 matrix using cofactor expansion. And so what is cofactor expansion? What cofactor expansion is that when we go along a row or a column, we can use these values here to tell us how we're going to make these 2 by 2 matrix that are going to give us the same determinant. So a quick example here, say we have a 3 by 3 matrix like this, and we start using cofactor expansion, we can pick any row or any column, but a lot of the time it helps to be strategic. We can pick values that make our life easier. So I'm going to pick this row here, which is going to make sense in 1 second why this is so helpful. So the process for cofactor expansion is first, we take whatever value is the first value in our row or column. So in this case, it's 1. And then we multiply it by negative 1 to the power of whatever the row and column are. So this is the first row and the first column. So it's negative 1 to the power of 1 plus 1. And then we're going to multiply it by the determinant, which we can represent using these lines, the determinant of everything that's left when we ignore the row and column that our value is in. So this value that we're using is 1. We can cross it off like this, ignoring the row, and cross it off like this, ignoring the column. And so what's left is right here, which is 2, 5, 3, 7. But this isn't just the only thing you need to do. You need to repeat this for every value in your chosen row or column. So next we're going to go on to this value here. We're going to go plus 0 times, this is negative 1 to the power of, this is still column 1, but it's now row 2. Negative 1 to the power of 1 plus 2 times the determinant of everything that's left over. So we can cross this off and cross this off. So it's times the determinant of 1, 4, 3, 7. And now we repeat this again for the final value of our matrix, which is 3 here. So now we're going to do plus 3 times negative 1 to the power of, this is the third row and the first column, 3 plus 1. And then when we exclude this 3 here, we're left with the determinant of 1, 4, 2, 5. And so you see how we've taken this complicated looking 3 by 3 matrix and broken it down into a whole bunch of 2 by 2 matrix, which we know how to do very easily. The next thing that's important to notice is that because this 0 is here, we don't really care about what the determinant of this is because it's getting multiplied by 0 anyways. So we can ignore it. And so if we're able to pick a row or column that has lots and lots of zeros, we can skip a lot of work because we already know no matter what the determinant is, it's going to be 0. And so we're going to do an example that shows us just how powerful this is. So we have this big giant 5 by 5 matrix. It looks like if we're going to do cofactor expansion, when we do it along any of these rows, what we're going to end up with is 5 different 4 by 4 matrices. And each of these 4 by 4 matrices, we're going to have to do cofactor expansion on, just like we did before. And when we do cofactor expansion on these ones, each of these is going to give us 4 3 by 3 matrices. And then, just like we did up here, once we have a 3 by 3 matrix, we're going to have to do cofactor expansion on this 3 by 3 matrix. And once we do cofactor expansion on this 3 by 3 matrix, this is going to give us, each of these is going to give us 3 2 by 2 matrices. And so by the end of this, if this gave us 5 4 by 4s, and this gave us 4 3 by 3s, and then that gave us 3 2 by 2s, we got 5 times 4 times 3, which is going to give us 60 different 2 by 2 matrices that we need to find the determinant of, and multiply it all together and add it up, which is just going to take way too much time to ever get done in any sort of feasible way. So we need to be smart and strategic about how we pick the rows and columns that we use. The beauty of using cofactor expansion and determinants is that if we add or subtract a row or column from another one, it doesn't change the determinant. So if I take, for example, this row here, or this column here, and I subtract it from this column here, that's not going to change the determinant. But what it's going to do is make our lives a whole lot easier. Because if we take 2 and we subtract 1, we're going to get 1. But now if we take 1 and we subtract 1, we're going to get 0. 1 and 1 is 0. 1 and 1 is 0. And this last one's going to give us 0. So just like we talked about before, we now have a giant row of all zeros. So we can do cofactor expansion along this column here. So we're going to go just with our steps like we talked about before. We start with 1 is our value here. So we get 1 times negative 1 to the power of 1, 2, 3, and 1. So this is the third column in the first row. Negative 1 to the power of 3 plus 1 times the determinant, which we can write using these bars, of everything that's left. So we can cross out this row and cross out this column, and we look at all the values that are left. And so what this gives us now is we have the determinant of 1, 1, 1, 2, 2, 1, 1, 7, 1, 1, 2, 2, and 1, 1, 1, 7. So now, instead of ending up with 4 different 3 by 3 matrix or 4 by 4 matrix, we only end up with 1, because when we continue to do our cofactor expansion, if we look at our next value, it's just going to be plus 0 times negative 1 to, this is going to be 3 plus 2 times the determinant of a whole bunch of stuff. It's going to give us a whole bunch of values. When we cross this off, it's going to be 1, 1, 1, 7. But it doesn't matter because we're multiplying it all by 0. And so we can effectively just ignore it. So we don't have to worry about this 0 here. We don't have to worry about this one. We don't have to worry about this one. We don't have to worry about this one. And so we've saved ourselves a lot of time because instead of having to calculate 5 different 4 by 4 matrix, we only have 1. And now we can use this exact same trick because you notice that this row and this row are very similar to each other. And so if we subtract column 2 from column 3, what this gives us is 1 minus 1 is 0. 1 minus 1 is 0. 2 minus 1 is 1. 1 minus 1 is 0. And so this piece over here, we can just write 3 plus 1 is 4. Negative 1 to an even number is even. So we really just have 1 times this determinant. So we're going to ignore it. And we can now do cofactor expansion again. We start with our 0. It's going to end up being 0. This is going to be 0. This one is going to be 1. So we get 1 times negative 1 to, this is the third row and third column, negative 1 to the 3 plus 3 times the determinant of everything that's left. So we can cross off this row and column, and what we get is 1, 1, 2, 2, 1, 7, and 1, 1, 7. And this last cofactor expansion value, 0 here, is just going to give us 0 again. So now already, we've taken this big giant 5x5 matrix, turned it into a 4x4, which we've now been able to turn into a 3x3. And so this is just going to end up being negative 1 to the power of 6, which is 1. So now we figured out the determinant of this big matrix up here is the same as the determinant of this small matrix. And again, we're going to do the same thing. We can keep doing our tricks here. We notice that this column and this column are very similar. So we're going to take column 2 and subtract it from column 1. So we're going to end up with the determinant of 1 minus 1 is 0, 2 minus 1 is 1, and 1 minus 1 is 0. So now we're left with the determinant of this matrix. And we're going to do cofactor expansion along this column. This is going to give us nothing. This is going to give us 1. So we're going to have 1 times, this is going to be the second row and the first column, so negative 1 to the power of 2 plus 1 times the determinant of everything that's left. So this is the determinant of 1, 2, 1, 7. And so this is going to be negative 1 to the 3 is negative 1, so it's going to be negative. And if you remember before, we know how to take the determinant of a 2 by 2 matrix. It's just AD minus BC. So we multiply this diagonal together. You're going to get 7 times 1. And then we're subtracting this diagonal, minus 2 times 1. And so what this is going to give us is negative 7 minus 2, which is just going to give us negative 5. And so we've taken this big giant matrix and we've reduced it down from a 5x5 to a single 4x4, a single 4x4 to a 3x3, and then a 3x3 to a 2x2, which we know how to calculate the determinant of. And it gives us our final answer of negative 5. And so that's how you take a really complicated matrix and use cofactor expansion to find the determinant.